2 minutes ago we discussed the many faces of Z2. Or first we got this cyclic group of order 2, which was isomorphic to Z2, and then we saw this in many other versions, and one was acting on functions of f of n variables, doesn't matter, in this way that OE, one group element, just mapped the function to itself, and OP, the other group element, mapped f of x to f of minus x. So we just get a minus sign here in the argument. Now, in the context of this example, let's consider some special functions. So, special functions fe and fo. And I want them to be such that OP applied to FE evaluated at x is FE of x. So that's not true for all functions. Recall that OP did just this here. So we got a minus sign here in the argument. So FE is a function for which f of minus x is f of x. And FO behaves as follows. When we apply OP to FO, then we get minus FO. So now you see why I called them E and O. That was for even and odd. So these behave in a special way under the group, and the group acts on them. We could also say that this function FE here is invariant under the group. Okay, now let's go on and consider this integral here. Integral over all of Rn Fe of x complex conjugated times Fo of x. Well, of course, this integral will not exist for any function of n variables, but let's say we chose some Fes and Fos, such that these integrals down here exist, and the Fe and Fo have these properties here, they are even and odd, then we know immediately that this integral is 0, because if we change variables here in this integral from x to minus x, we just get an overall minus sign here. So it's equal to minus itself, means it's 0. Okay, this is called an orthogonality relation. And in physics applications of groups and representations, this would be called a selection rule. Of course, here in this example, this is just making really elementary things look difficult by introducing lots of notation. Nothing happened so far, but the nice thing is that this will generalize. If we go to other groups, not just a group of two elements, we will have functions that behave in a special way, and there will be orthogonality relations between functions that behave in different special ways. That's something we will see later. And there's one more thing we can do also in more general. Let's do it here in this example. Take some function f, and then we can always write it as a sum of an even and an odd function. Of course, you know how we do this. Just define Fe, let's say Fe of x as 1/2 f of x plus f of minus x, and f odd is 1/2 f of x minus f of minus x. So now these functions here, they have this special behavior which we want, and the general function, the arbitrary function f, is a sum of these two. And that's also something which will generalize. So we will be able to expand arbitrary functions in functions that transform in a special way under the group. This is the outlook. That's something we will see much later.